Okay, here the point is that uh, in big data algorithms, because in MPC algorithms, because no machine can see the whole input, you can imagine that it's highly important to like discard less important elements. So pruning, okay? So that's why you have prune here. But how do you prune that? I mean, so we are going to sample some elements, and by comparing each element to the sampled elements, we are going to prune. Okay, that's the idea. So okay, so let's actually let me start with the simplest example, top K selection. And if you don't before, although like I wrote this tutorial, uh, starting with the general framework, I think it's still like helpful to understand this simplest example. Okay, so top K elements, it's in chapter 4.2. So what do we do here? So we are n elements, right? And our goal is choose top K elements. Okay. Oh, it's super simple problem, right? If you have enough memory, what do? You just, read through the whole algorithm and hold the elements, and you only keep the top K, right? You can even you can even design simple string algorithms. You just scan all like elements, one by one through all elements, and then so only keep top K elements and discarding others, right? So yeah, if you have enough, if you can see the whole like elements, not a problem. But again, in MPC algorithm, every machine is as a memory, which is sublinear memory in input size. Therefore, it cannot see the whole input. So what should you do? Okay. Yeah. So uh, let me slightly restate. Let me restate this simple algorithm. Right. So yeah, you can scan, or what you can do is that, hey, just you can think of this as a greedy algorithm, right? Uh, in each iteration, choose the top element and remove uh, remove it, right? So you can repeat this by k times, right? A super simple algorithm, right? It cannot be simpler. So what do we do here? I mean, we solve this problem, right, using divide and conquer, the partitioning algorithm, right, in the previous chapter. But let's try to use different, some like overly complicated way, but still like it'll be useful. Uh, so what do we do? Um, so we have we still have this n elements, right? It's n elements partitioned across p machines. Okay. So what we do, instead of keeping top k elements in each machine, so we are going to sample from x. Okay. Then, anyway, this is our greedy algorithm, G. Let's call this G. Okay. So what do we do? Well, um, so we are going to apply G over it. So we get sample I, sample like some, S1, S2, like this SP, right? These are, we get some sample from X1, some sample from X2, excuse me, and some sample from SP from XP. Okay. And this is only small sample. You can aggregate into one machine, right? So let's say that it's just say, and then what do we do here? We're going to apply the G over S, right? Excuse me. G over, S is just S1, S2, all this union, right? Okay. Then, then as a result, we are going to get top K elements in, in the sample. Okay. By the way, we can do it in parallel, right? Because sampling is so easy. So the only thing I need to tell each machine is that, hey, so sample each element with a certain probability. We just do it independently. It doesn't need any communication across machines, right? Using samples, each machine samples some elements and then sends out the sampled elements to a specific machine. Okay. And then because the whole samples are small, so we can run this greedy algorithm on the sample. And then as a result, we're going to get top K elements in sample. Okay. Now what do we do? Like we are going to send these top K elements to all the machines. Think of this as a filter. Okay. Like again, this filter is small size because it's only K elements, right? So what do we do? Okay. So we are going to test. Okay, so think about some element here. Okay, so we're going to test if element E is useless using the filter. Okay, so what I mean by useless is the following, right? It's useless if it's not going to appear. Of course, it's not going to use. It'll be useless if it's not going to appear in my final solution. But I need to define this useless only using this filter, right? Because I mean that's all I have here on each machine. It has access only to this X1 and this filter. Okay, so specifically, we are going to the following. Hey, let's say that GS, right, is same as GSE, right? Yeah, by the way, here, you see that, okay, these are top K elements. So let's say top K elements are E, say this is S prime. Okay. So and it's easy to see that, GS is equal to GS prime, right? By, obviously, right? Because S prime is the top K elements in S. Okay. So like instead of this, you can actually, let's do the following. So this is the test. Hey, uh, should I keep this element E because it could be used for later, or should I discard it because there's no way that this element would appear in the final solution? Okay, so how do I test it? So if when I run the algorithm, okay, on this S prime, right? Okay, if I get the same result with element E, then I'm going to say that E is useless. Discard. Or like prune E. Okay. So we discard lots, hopefully we discard lots of elements here. And then the remaining elements are, and then like many points will be just, just deleted by. And then we'll have a hopefully we'll have a much fewer element. Excuse me, my writing was so bad. I'm sorry. Now we have a hopefully much fewer elements on each machine because we filtered out many elements. Okay. I mean, if necessary, we repeat this process, get on a sample, and then construct some test or filter, and then on each machine we filter out, prune out the some elements, like useless elements, and then at the end of the day, I have like very few elements left in total, so aggregate all of them and dump into one machine and solve the problem. Like, so for example, here you can use the same grid algorithm, right? So we are going to actually use the R1, R2, RP, and plus sample as well. Okay. So I want to show like what's really going on here. So by seeing the picture here. Okay, so let's move to the next page. So again, this idea is more here, because anyway, I'm not going to test this topic in the final exam. Therefore, I think it's the high level idea is more important. I think it's worthwhile actually, remembering this. You forget the method, but I think the idea is still very useful. So okay, so what do we do? So let's like zoom in like one machine. So it has xi. Okay, so it has xi, and like probably even better. So A1. So say these are the let's use X. Oh no, A is better. So suppose like let's visualize this by use for illustration purpose. So like let's like I like order all the elements in decreasing order. Okay. Then I mean obviously I what I care is about like this phi, top k elements phi. This should be my final solution. Okay. And in this paradigm, sample and prune, we want to make sure that we never prune out important elements. Namely, we should never prune out any of these top k elements. It's highly important because if I prune out any of these elements, then my solution will be incorrect. And what's going on here? So okay, think about this, right? So like I'm sampling, right? So actually it's yeah. So what I'm doing is I first sample some elements. So say like say three A3 was sampled and some other points sampled and so on. These are sampled points, say. Many points are sampled by, but anyway, um now okay, so what am I doing here? This is set S. Okay. And what I'm doing is this GA. Let's test if G S is equal to GS union E. If this is the case, E is useless. Right? So what does this mean? Well, here, it outputs the top K elements from S. Okay. But now, okay, so let's try to output top K elements from S and E, but I didn't choose E, right? So what's happening is like so E is okay, say these are like, say B1, B2, like BK, right? These are the top K elements in So say here S prime is oh, noise. I'm sorry. Suppose this is top, this is subset top k elements in S. Okay, so then you know if this happens, then like I'm for example, like I'm looking at this element E, right? So by comparing this element E to sample A, this E element E didn't even make it to the final top K even in S. Okay, then what you can imagine is this, right? What you can infer is this, right? Then G, right? Or E is not in top K elements in X. Okay, again, element E could not make even in the final K only from S. Even if you only look at only a few elements, right? These like elements, it was not in the final K, top K. Then it has no chance to be in the top K in the whole set of elements. Okay, so if I discard the y by this method, right, then I can be sure that it must not belong to the right solution. So the pruning will be correct. So this means that pruned. This is one thing. The next one is that okay, so like like this filter, right? This tester, right? Sure that you know it should prune many elements, right? It's important. Many like, useless elements, right? Because otherwise, like after applying this filtering, right? If you still like too many elements, right, then I cannot still like aggregate these elements into a single machine. Therefore, what I further need to ensure is that the filter is good. It just filters out many useless elements. But at the same time, you should never prune out. We okay, so I guess it's better. We never prunes out important elements. Right? These two are the key, like key aspects, key ideas in this approach. Okay, now you see why is it true? Because see, what's happening is that if you look at this picture, like okay, these are the top key elements right here, right? In S. So like I'm gonna like I'll definitely throw out all the other elements by name the behind the case largest element in the sample. Okay, so yes, I mean if my sample size is super big, then okay, there's a trade-off here, right? So if sample size too small, if the sample is too small, then I cannot filter out too many elements. Okay, so like think about like a very extreme case, right? So say like this is A1, like A2, like AN, right? Suppose suppose my sample size is like really like small, therefore it's very sparse, right? Then I can only filter out basically very few elements, right? That's not good. Okay. But if my sample is too big, then the problem is the sample, right? Because I need to get the sample. I need to dump the sample into machine, right, to construct this tester, this filter, right? Therefore, the sample size should not be too big. And if the sample is too big, I cannot construct this filter on a single machine. If sample is too small, then I cannot filter out many elements. So we are going to find like the right size. Does this make sense? It's a very high level, but uh, but like let's keeping this keeping this simple example in mind. Let me just talk about this algorithm framework. Uh, this is the algorithm in the lecture notes. Sorry. The sample and prune framework. So here R denotes the remaining set. So here U is the whole U is the whole set of elements. So we are going to only focus on the problems where we want to choose a subset of like edges or like elements like that. Okay. And then and then ensure the sample size is 0. Sample is not empty. And then this is what I'm going to do, right? So like we are going to repeat this, right? If the until the remaining elements, until we have a few only a few remaining elements. So M is kind of threshold. So if you have more than M remaining elements, we're going to repeat this. We sample each element from the remaining elements independently with probability, roughly speaking, M over R. Okay, and add to S. Okay, and then as we discussed before, so what you do is that we're going to build like a very simple tester. Okay, so it's a we put like this G and S. G is the greedy algorithm. S is sample, and for every element, we this tester will say, hey, keep it or prune it. Okay, and what does this tester do, right? So is prune, right? Filter out. If and only if we get the same result when you run the greedy algorithm with and without the element. Okay. And then so we are going to of course remove we have to remove all the elements by pruning. Okay, that's it. And then at the end of the day, what we do, we do just return. We are going to run the same greedy algorithm on the remaining elements and the sample. Does the algorithm make sense? I hope that the illustration using type K elements help you understand this algorithm framework. Okay, I want to make some point here. So so this sampling can be done in parallel because it's a very simple thing, right? So this is the probability. The reason that we are doing is this is because I see we have a roughly R elements, right? Okay, and if you sample each point with probability roughly M over R, then you get you sample M elements in expectation. Okay, M is the memory size, right? So you cannot sample more points because if you sample more, then it exceeded the you know the it exceeded a machine's memory size capacity. Okay. Here you see like this tilde sigma is, but ignore that. It's not very important. Because it's a probabilistic sample, like to make sure that you don't sample too much or like some to get some high probability. There's some hidden log factor, but that's not really important. Okay. Anyway, the point is that here we sample independently every each point, but not too much. Okay, that's why we cannot just sample too many points. We cannot set the probability too high. And then as you said before, so this is a test. Do you get the same algorithm? Do you get the same result with E or E without E? Then E is useless. Okay. Then we remove all pruned out elements. And at the end of the day, we run this algorithm, greedy algorithm again, on the remaining elements plus sample. Okay. That's the whole framework. So like to understand, okay, just we define the usefulness here. So this okay, this is this definition is like this definition is why is this? I'm sorry, useless. Okay. And then here, basically the only property we need is this monotonicity, right? This definition. You can think of G as a function because algorithm, but it's a function, right? G is a monotone. Okay. Uh, so we define this monotonicity here. G is monotone. Okay. Suppose it was useless. It was useless for a small subset S. Okay, record the example. So E was not even top K elements of S. Then it must be useless as well for the entire set of elements. Then again, in the example, it cannot be the top K elements in the whole elements. Is definition clear? The monotonicity. Okay, and yeah, so so I think the memory requirements we satisfy. It's easy to see that we satisfy the memory requirements because the sample size is small, and then yeah, so sample size is small, and then therefore we can construct this tester, and we broadcast the tester to all the machines, And in every machine, it just filters out many elements. So, you know, we always, keep this, we always meet the memory requirement. That's fine. Okay. So then now we want to argue two things here. One, never, never discards. We never discard an element, any element in the optimal solution or the correct solution. Because sometimes it's optimal because we want to minimize or maximize, or just sometimes it's correct answer because it's because it's just like for example top k, right? It's either correct or not, right? And then like you also want to ensure that it runs in small number of rounds, like so how do we get this? How can you ensure that it runs in small number of rounds? Okay, to show this, it discards many elements in each iteration of while loop. Okay. If you show these two things, it will be done. Okay. The first one is kind of easy. We never discard an element in the optimal solution. Okay, it just directly follows the monotonicity. Okay, so because you know uh is by definition monotonicity. Is that clear? I mean, we never discard an element in the final solution. This is the important part. So do you see why we never discard an element in the optimal solution, the final solution? Is it good or no? I need feedback here. Yeah, I just because I don't hear any feedback. So yeah, you see, this is what you want, right? This is if you have a simple greedy algorithm, we run greedy algorithm on the whole this universe of elements, then we get it. We are done, right? But what it did was that hey, so we discarded right. We discarded an element E only if G of U is equals ZU union E, right? So okay, sorry, I'm sorry. What am I talking about? Sorry. G of S E is the same as G of S, right? Okay, and then uh, by monotonicity, uh, okay, so in other words, we discard the element, and then what does it mean? It means that G of S union E was equal to G of S. Okay, that's by definition. That's by the algorithm definition, right? And by monotonicity, it means that G is uh, um, I guess I should be clear here. So it's E. So okay. So this is a subset. This is a subset. This is a subset of E. This is a superset of S, right? So okay. So by monotonicity, right? So this is true. So E is not useful at all. Okay. So it means that it was okay. It was safe to discard the element E. Okay, we didn't lose anything. So instead of U, we can just focus on U minus E. So it was a good decision. Discard E. Okay. So this is why we never discard an element in the optimal solution or the right solution. The first one is kind of easy, but the second one is a bit tricky. Actually, let's before we talk about this, right? See, this monotonicity property, right? Monotonicity. Um, you can check this problem, this property for type K elements, type K application, and also for minimum span tree. Okay, so what does it mean, right? I mean, we kind of we implicitly discussed this monotonicity in the previous chapter. So what it means is that, hey, G, okay, suppose Z, right? Suppose we have like E prime and E, right? Then E prime is subset of E. Then what you know is this, right? So I mean, this we argue this by okay. So what this means is that I'm just repeating this because in case I think in case this can it's worth listing this using this filtering argument here. This means that E is not safe here, right? Because E remember that E is E belongs to minimum span tree if and only if is E is safe, right? So it means that E is not safe, right? Okay, E is not safe. Okay, so and we argued that hey, this implies that E is the heaviest edge on some cycle C by. Then okay, then again, this implies that okay, so E E will be, but this cycle C will also appear in superset E. Therefore, E will be it heaviest edge on some cycle appearing this graphic constant of edges E. Therefore, this must be true. This implies that E is the heaviest edge on some cycle C, which is a subset of E, right? And this implies that E is not safe in the crops of V and E, right? So this implies that, okay, so yeah, so, this implies that this is true, right? Because then in the case E is not chosen. So anyway, the point is that here, the monotonous property is key idea here. So, okay, now second one. So now we are going to talk about the how effectively we can count the elements. This is actually a tricky part. So I'll be a bit sloppy here because the equations very formally take time, and then it's like I think it's less important to focus on the formula than understand the high level idea. Okay, so okay, how should I start here? Okay, here's my goal. Okay, so say sampling probability is 1 over, say, n. Let's say this 1 over square root n. Okay. In the lecture note, it says that delta it's n over n to the 1 minus delta, but let's say delta is half. Okay, then in the case we'll have 1 over square root n. Okay. Then the sample size y will be square root n in expectation for sure. Okay. Then uh, then remember that we learned this chain of bounds, right? So when we expect, because we sampled every point independently, we can show that the probability the sample is say sample is like very small. I'm putting some like some like arbitrary response. So I say like it's two square or some. Anyway, it's very small. Yeah, here again the what I'm saying is that, hey, the sample size will not be deviate too much from its expected size. Okay. And then no, actually no, actually yeah. Okay, so let's assume that S is actually let's assume it's a square root n for simplicity because it's not, it doesn't really matter. Okay, what I want to show the following: the probability. We are interested in how big this R is. Remember that R is the remaining elements. After filtering out, R is the remaining elements. Okay, we want to show that R cannot have many points. So we want to show that the probability that this is big. So like for example, it's 10 times k times root n times log n. Don't worry about this log n like 10. These are like really important. This is not very important. Okay. And we are going to show that this happens with say probably say uh, one of n or one of n. Some very unlikely. Okay. So why So if we show this, that then it will be basically done because, okay, we start with n elements. Then after sampling, like after filtering out, we'll only have roughly k times square root to n times log n elements, right? I mean, assuming the k is small, then it's a big improvement from n to k times square root to n. So yeah, if you show this, then it would imply that we effectively filter out many useless elements. Therefore, this framework is effective. Okay, so how do you show that this is very unlikely to happen? So so to okay, so let's think about this, right? Let's fix R here. I mean, R is a stochastic. It's a random set. Okay, but let's fix some R. So it can be something, some subset, but let's fix R. And then like here, but here R such that the size is big. Okay. And what you want to show is this. If we sampled any element, so this means that, right? This means that the sample intersects with R, which means that we sampled at least one element from R, right? If we do that, then if that happens, then um, this is basically what you want to show. Okay. So instead of using like a notation, okay, let's go back to this example, right? So let's go back to this top k elements example. Okay, it's very intuitive. So okay, how should I explain this? Okay, so what are the remaining elements here? So these are kind of these are discarded by. Okay, and then these are the remaining elements, right? Because these were sample. And then okay, these are like top k in the sample, right? And we discarded all the other end elements because they were these were even smaller than the k is the largest element in the sample. Okay, that's what happened, right? And okay, so here uh, okay, so suppose like we had a sample here. Suppose we had the sample say E. If E is in the sample, right? Then what happens? Then G of S G of S. So actually, let's see. So like you can't be. Let's just do this, right? G uh S union E. Okay, so S was sample, but so suppose you had another element E in my sample. Okay, then this would be different from G of S. Would you agree? Like in this case, what happens, right? Then instead of this, right? You're gonna choose E, right? In by using greedy algorithm. So like this will become different. This will be different. Okay. Then what happens here? What happens is that hey, instead of discarding these elements, right? You're going to discard these elements, right? Because now because you are going to choose in G S of E will be these elements, right? Not including this last one. Okay, so this R cannot be the same. So this and then okay. Do you see why this is true? If you sample okay, so if you sample any point, uh, so okay, so let's say that. So let me slightly more formalize this for any element E in R. Okay. Uh, any element in R, the the remaining elements using tester uh, G of uh, S E will be different from the remaining elements using tester G S. This is a claim. I mean, it's the tutorial says a lot, but this is what's really happening. Remaining elements using tester will be different from the remaining elements from using tester GS. Okay, so if you sample the element E additionally, the result will be different. You cannot have R. So okay, this is important. This is actually the key part. The remaining things are kind of math. Do you see why this is true? Here I'm just illustrating the idea using this top K elements, example, but this holds true in general. Like assuming that only monetized property, you can show the same thing. And what's the idea here? So the interesting thing is that hey, if R is really big, right? Hey, come on, like I then there's a good chance that I'm gonna sample some points here from R, right? So then it's very unlikely to happen to have this R as a remain set. So again, if R is big, can it happen that I have like this in a large set R? It's very unlikely to happen. Why? Because if I sampled any element from this R, okay, then I cannot have R as a remain set because the tester, the filter we construct will be different. I hope this makes sense. Okay. Then okay, then now we can check like what's the probability that What's the probability that S and R is empty set? What's the probability we never we okay? So even though R is big, what's the chance that I'm gonna say I sample nothing from R, right? So it's kind of easy because you see, our sampling probability was 1/square root n. Therefore, this uh, the probability of sampling the point is not in R is exactly 1 minus 1/square root n, right? Oh, excuse me, sorry. Uh, okay. Sorry. Yeah, I think there was some mistake here, but so okay, R is big, right? So like basically k times the square root n times log n, 10 divided by n. This is the fraction of the elements that are in R, right? So when you sample up element, what's the chance that this is the probability that uh, sampled element is not in R, right? Okay. But then what happens here, right? We do this. What sample size? Sample size script n, right? So like because we sampled every point independently, this will be the case, right? So then it's using the magic formula one plus x is m plus e to the x, right? It'll be exp minus 10 times k script n log n times script n divided by n. Therefore, it'll be this becomes n exp minus 10 k times log n, right? So it's very small. It's like log n becomes 1 over n, so it'll be n to the inverse of it, inverse of n to the 10 times k power. Okay, good. So like we showed that it's very unlikely to happen. So like when R is big, it's not going to happen probably. Okay. But now here's a very tricky thing. This is probably the other part here. Um, Typically you can just apply union bound, right? So you can try this Troman's attempt. So you can try the union bound over all R or like big R's, right? But that's too many, right? See, like it's a anyway, like think about all subsets, right, of R. Like it's 2 to the n, right? Like anyways, it'll be exponentially many. Okay, so I mean it'll be more than like 2 to the n divided by 2. So anyway, this is if you because there are so many like okay the the problem is that number of big R's is super big, super big. Okay, so if you take union bound over all such R's, like it'll be 2 to the n minus 1, times n to the 10 over k. I mean, still it'll be more than way bigger than 1. So you cannot say that this bad event will unlikely to happen. Okay, so what it can actually do is the following. The key observation is the following. Remember that why? So this, right? So remember that GS is equal to GS prime, right? I mean, S prime is top K elements in the sample. Okay, so it's the same. So in other words, yes, I mean this you can think of this filter. You can compactly summarize this filter using K elements. Okay, and what does this mean? So when you say, okay, we said that the remaining elements we're using tested this will be different from G of S5. I mean, it also implies that testers are different. Okay? And what I know is that every tester can be characterized by K elements. Because, G of S is equal to G of S prime. So what this implies is that number of, distinctive testers is at most what? N choose K, right? Because, every tester can be characterized by n most K elements. Therefore, the number of distinct testers will be N choose K. Okay? Then what this implies that each tester there are n most N choose K different possible R's. Right? The remaining possible, the remaining set R, it's stochastic, it's different. But however, the point is that there are N choose K different possible remaining sets. So therefore, you can only take a union bound. So union bound over distinctive big R's, right? So then what's that? Right? It's N choose K times 1 over N to the 10 times K, right? So it is what locally speaking, it's what? And it's almost N to the K, and this is like a 1 over K. So it's much more. It's way smaller than like say assuming the K is big, the K is like 2 or 10, that is to some something like this one. So that's it. So we can show that big R will very unlikely to have big R's. Do you have any questions about this? Okay, so yeah, I'm not going to cover the other two applications, but I'll briefly touch on the K center and the level of today's lecture. So here is very interesting. So, we can revisit the case and the problem, right? And here the interesting thing is that we can get two approximation using uh, sample and prune, right? Uh, you know, in contrast, we obtained only 4 or 8 approximation, right? Using partitioning, right? I'm not going to details why the analysis because the analysis is a bit tricky. But I want to give you some intuitions why we get better result as opposed to what you get using partitioning framework. So the reason is the following. I mean, remember that when we did the partitioning and solve the k center problem, right? So we had like this xi, and we solved okay, good. We solved this problem, right? We solved this sub problem, right? Only using xi. Okay, so we run like this greedy algorithm, like not greedy algorithm. So we use like two approximate algorithm on this xi, and we solve it, right? But now, okay, but the problem was that when it chooses k centers out of xi, like this was too local decision because without seeing like all the other all the other versus nodes, you made choice. You made a k. You chose k elements, right? But in contrast, what's happening in this sample and pruning is this. We gotta basically we gotta sample, right, from all motions, right? Okay, and then we really focus on what you can safely discard. What can we safely prune? All right, and this was based on the global. So we just use hey, G of S, right? Is if we have this, then we can filter it out. Okay, then we can just delete this element E. And here we ensured due to monotonicity. Due to monotonicity, so E should never appear in the global solution, right? So we explicitly ensure this. Okay. So at the end of the day, what happens is that we still kept all we only discarded the elements we were completely sure about completely sure that would not destroy the global solution. And the only thing is that so this sampling by sampling, we kind of reduced it. We also filtered out many elements, so we were able to uh, 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 filter out many elements. Therefore, we had a few round algorithm. So okay, so let me wrap up here. So there are so the takeaway points are the following here. So we learned two major techniques, right? Partitioning and sample and pruning. So sample and pruning is kind of more global, and it's like very kind of cute technique because instead of trying to solve the problem, right? Hey, what choose, forget about what to choose, but focus on what you can safely discard. Okay, it's a really takeaway message. And then, what's like a simple like way to test it? Okay, we have a very simple way, right? So we have some like certain like sequential algorithm, like say like in top k elements, right? If if the element E would not change your outcome, probably is not useful. It must be useless. That's a very like natural way of constructing this filtering or like a test algorithm, right? And then that's the only thing. And here the only thing we need to we need to have is that monotonicity. Then you can use the framework. Yeah, but like still like partitioning algorithm is very useful because sampling actually takes some time. And partitioning algorithm is it's even simpler, right, to implement it. So therefore, like both approaches are kind of have pros and cons, but I think that's they are really like a common techniques that you can use in your life. Okay, so if you're interested, you can read the details of case center clustering, but it's a bit tricky because you kind of need to like argue that why how you can maintain some ordering in the greedy algorithm, but you can do that. And also, if you're interested, you can read the subordinate optimization problem in the next subchapter. Okay, I'm going to finish it now, and then tomorrow I'm going to move to game theory, algorithm game theory. Okay, which should be a new topic that factors in the participants' selfish behavior. Okay, so thanks, guys.